The universe didn't begin from nothing. Nothing itself was never allowed to exist. Before space, before time, before anything you've ever been told had a starting point, something was already there. Today we're going to find out exactly what existed before the universe was born. Now, let's begin. The universe didn't begin in darkness. It didn't begin in emptiness. It began without a before, because time itself was the thing being created. And here's what makes that truly staggering. This isn't philosophy. This is a mandatory mathematical conclusion from the most rigorous physics of the 20th century. In 1970, Stephen Hawking and Roger Penrose proved something that could not be argued away. If general relativity is correct, and every experiment we've ever run confirms that it is, the universe absolutely must have had a beginning. Not probably, not likely, must. It's a theorem. And at that beginning, every equation in physics walks up to that moment and collapses. Not because the equations are wrong, but because they were built inside the universe using the logic of the universe to describe the very thing that created the universe. That's not a flaw, that's a boundary. And from that boundary, every real question begins. Most people think of time the way they think of the ground beneath their feet, solid, permanent, always there, something the universe simply sits on top of. Einstein showed us that picture is completely wrong. Space and time are not a fixed stage where cosmic events play out. They are physical things. They bend near massive objects. They stretch when the universe expands. They slow down inside strong gravitational fields, so measurably, so precisely, that GPS satellites orbiting Earth have to correct for this effect constantly, or navigation systems would drift by several kilometers every single day. Time is not the backdrop to the story. Time is a character in it, which means time can be warped, which means time can be created, which means time had a beginning. And everything we associate with before cause-effect sequence history had no place to exist until that beginning happened. This is where the human brain hits a wall it was never built to climb. We are wired for causality. Everything in our experience has a history attached to it. You exist because your parents existed before you. This morning arrived because yesterday happened first. That entire chain of reasoning runs on time the way a fire runs on oxygen. Remove the oxygen and the fire doesn't burn poorly. It doesn't burn at all. Remove time and causality doesn't work slowly or imprecisely. It simply doesn't work. So when someone asks what caused the Big Bang, they are unknowingly using a tool, causality, that only functions inside time, to ask about the moment before time existed. The question sounds perfectly reasonable. It feels like it deserves an answer, but the machinery needed to process it wasn't running yet. Hawking captured this with an image that cuts straight through the confusion. Asking what happened before the Big Bang, he said, is like asking what lies south of the South Pole. It sounds like a legitimate question. It sounds like there should be a place there waiting to be discovered. But the South Pole is where the concept of south reaches its end. Direction terminates at that point. There is no more south beyond it, not because the territory is unexplored, but because the concept no longer applies. The same thing happens with before at the origin of the universe. Time ends there, going backward. The word before doesn't point towards something unknown. It points toward nothing because the pointer itself was just invented. But here is what physics doesn't tell you right away, and it changes everything. The collapse of equations at that boundary is not a dead end. It is a door. General relativity breaks down at the beginning of the universe because it was never designed to handle the quantum world. It describes reality at large scales with breathtaking precision, but at the extreme densities of the universe's very first moment, quantum effects take over completely. And quantum mechanics applied to that same boundary doesn't stop. It keeps calculating. It looks straight through the place where classical physics gave up. And what it finds on the other side is not emptiness, not silence, not nothing. What it finds is something restless, something active, something that turns out to be the most surprising discovery in the history of science. So the question becomes worth asking in a new way. If time began with the universe, and cause requires time to come before effect, then what kind of process could produce a universe without needing a cause. In the traditional sense, the answer doesn't come from speculation. It doesn't come from untestable ideas or abstract philosophy. It starts with something almost insultingly simple: a metal box, a vacuum pump, and a refrigerator. Scientists built the closest thing to true emptiness that human hands could create. They expected to find nothing inside. What they actually found permanently destroyed the idea that emptiness is ever truly empty. If time began with the universe, what does that tell us about everything we assume about cause and effect? And is there any process in nature that operates completely outside of time? Take a container, remove every molecule of air inside it, cool it down to the lowest temperature physically possible, seal it shut. You've just created the most perfect emptiness human technology can produce. And what's happening inside that container right now will completely change what you think nothing means. In 1948, a Dutch physicist named Hendrik Casimir made a prediction so strange that most of his colleagues thought he had made an error somewhere. His experiment needed no sophisticated equipment. Two flat metal plates, polished smooth, placed parallel to each other inside a perfect vacuum with a gap between them thinner than a strand of human hair. No electrical charge on either plate, no magnetic field, no air, no connection of any kind between them. Classical physics was absolutely clear on what should happen: nothing. The plates should sit there in perfect stillness indefinitely because there was nothing present to disturb them. But Casimir's quantum calculations said something completely different. They said the emptiness itself would push the plates together. The reason is this: the quantum vacuum, the lowest energy state that space can occupy, is not uniform stillness. It churns with fluctuations with energy that appears and vanishes at every point in space, at every moment. These fluctuations come in all sizes. In the open vacuum outside, the two plates' fluctuations of every possible size happen freely. But in the tiny gap between the plates, only fluctuations small enough to fit in that narrow space are permitted. That means fewer fluctuations inside the gap than outside it. More quantum activity pressing in from the outside than pushing out from within. That imbalance generates a real, physical, measurable force that pushes the plates toward each other. Casimir predicted it in 1948. It was confirmed experimentally in 1997 with extraordinary precision. Today, engineers designing microscopic machines have to account for this force because at small enough scales it becomes strong enough to make components stick together without warning. Empty space is pushing on things. Nothingness has pressure. The second proof didn't require two plates. It required one atom. In 1947, Willis Lamb was studying hydrogen, the simplest atom in existence, one proton and one electron. Quantum theory made very precise predictions about the energy levels of that electron, and those predictions were excellent. But Lamb measured something the theory said shouldn't be there, a small but unmistakable shift in the electron's energy level, away from where every equation placed it. There was only one explanation: the space surrounding that atom was not empty. It was filled with virtual particles, pairs of particles flickering into existence and vanishing again so rapidly they couldn't be directly observed but real enough during their brief lives to collide with the electron, nudge it, and push its energy slightly off course. Lamb called it a shift. The Nobel Committee called it a discovery worth the prize in physics. Virtual particles fill every cubic inch of space in the universe right now, including the space inside your own body, constantly appearing and disappearing, impossible to catch directly, but impossible to deny. The third proof requires no equipment to appreciate: helium-4. A stable, ordinary form of helium refuses to freeze into a solid under normal atmospheric pressure, no matter how cold you make it. Cool everything else to the lowest temperature physically achievable, and it becomes solid. Helium-4 stays liquid. The reason is that quantum mechanics assigns every system a minimum baseline of energy called zero-point energy that cannot be extracted no matter what you do. You can remove heat, you can slow atomic motion to nearly nothing, but you cannot remove this residual quantum vibration built into the very floor of physical reality. For most substances, this floor-level energy is too small to overcome the forces holding the solid together. For helium-4, it is just enough. The quantum jitter at the ground state of emptiness keeps the atoms from ever locking into a fixed structure. The vacuum vibrates. It has always vibrated. It cannot stop. 3 experiments, 3 independent measurements, 3 separate confirmations of the same conclusion. And then there is the theoretical argument that makes it airtight. Heisenberg's uncertainty principle, one of the foundational laws of quantum mechanics, states that energy and time cannot both be precisely defined simultaneously. This is not a limitation of our instruments. It is a feature of reality itself, baked into the structure of the universe at the deepest level. If a region of space had exactly 0 energy, that would be a perfectly precise energy value. And a perfectly precise energy value is exactly what the uncertainty principle forbids. The universe is not merely incapable of producing absolute nothingness. The universe is physically prohibited from doing so. Absolute nothingness isn't just absent. It's against the rules. This completely reframes the mystery of cosmic origins. The question was never really how did something come from nothing? Because nothing total, absolute, perfect, nothing has never been a state that physics permits. The quantum vacuum is the closest approximation to nothing that nature allows. And that almost nothing is not passive. It is not waiting quietly. It is generating energy, producing virtual particles, and fluctuating constantly at every point in space, at every moment in time. Turns out nothing is the busiest thing in the universe, busier than you on a Monday morning with a deadline in 1 hour and your coffee still brewing. Which raises the obvious question, if the quantum vacuum never stops churning with energy and activity, why don't entire universes appear all the time? The answer is that the same mercurials governing virtual particles also govern larger fluctuations, and for most fluctuations, the borrowed energy must, to be returned, almost instantly. Almost. There is an exception, and that exception changes everything. If absolute nothingness is physically forbidden from existing, does that mean something has always existed even before our universe began? Yes. And in 1982, Alexander Vilenkin calculated exactly what that something was capable of doing. He wrote down the equations for a universe appearing from a state of no space, no time, and no matter. He worked out the probability. He checked his result, then he checked it again. The number he kept arriving at was not 0. And he sat with that result for a long time before he dared publish it. Alexander Vilenkin did not set out to prove that universes could appear from nothing. He set out to do what physicists do, follow the mathematics wherever it leads, even when it leads somewhere deeply uncomfortable. In 1982, he wrote down the equations describing a universe in a state of absolute 0 size. No space, no time, no matter, no fields, nothing in any sense that the word has ever meant. Then he asked what quantum mechanics predicted would happen to that state. And quantum mechanics gave him an answer he had to read. The probability of a universe spontaneously appearing from that state was not 0. A universe could tunnel into existence from nothing at all, no cause required, no time required, no prior universe required. Nothing needed to happen first. Because there was no first yet. To understand what tunneling actually means here, you have to understand what it means in the context where we already know it works. Classical physics says that if a particle doesn't have enough energy to cross a barrier, it simply cannot cross it. Full stop. But quantum mechanics says something different. It says the particle has a probability of appearing on the other side of the barrier anyway, not by going over it, not by breaking through it, but by vanishing from one side and reappearing on the other, without ever existing in between. This is called quantum tunneling, and it is not a theoretical curiosity. It is the operating principle behind every transistor in every electronic device on the planet right now. The semiconductor chips inside your phone function because electrons tunnel through barriers they classically have no right to cross. Without quantum tunneling, modern electronics does not exist. It is one of the most experimentally verified phenomena in all of physics. Vilenkin took that same mechanism and applied it to the universe as a whole. A state of nothing, truly nothing, not even empty space, has a quantum probability of tunneling into a state with a small but finite size. Once that tiny universe exists, even for the briefest possible moment, inflation takes over and expands it into a full-scale cosmos. No external cause, no prior moment in time, no creator needed outside the process. The universe is its own origin, in the same way that a quantum particle can appear on the far side of a barrier without any force having pushed it there. 1 year later, in 1983, Stephen Hawking and James Hartle arrived at a similar conclusion through a completely different path. Their proposal, known as the no-boundary proposal, describes what happens to time near the very beginning of the universe, using a mathematical technique that treats time as behaving like a spatial dimension under those extreme conditions. The result is that the universe has no boundary in time, no sharp edge where things began. It is like the surface of the Earth, finite, real, and yet without any edge or starting point. You can travel across the entire surface of a sphere without ever hitting a wall or falling off. The geometry simply curves back on itself. In the same way, the history of the universe curves smoothly into existence without requiring a moment of creation or a cause that came before. The question, what happened before the Big Bang, doesn't get answered in Hawking and Hartle's picture. It gets dissolved. The question assumes a boundary that isn't there. Both approaches arrive at the same remarkable place from different directions. A universe can appear without a cause, not because the rules of physics are suspended, but because the rules of physics applied consistently and honestly lead to that conclusion. And then there is the question of energy. One of the most sacred laws in all of science is conservation of energy. The total energy of a closed system never changes. If a universe appears from nothing, doesn't that violate this law catastrophically? The answer, it turns out, is no, and the reason is one of the most elegant results in all of cosmology. The positive energy contained in all the matter and radiation in the universe is balanced almost exactly by the negative energy of gravity. Gravity is an attractive force, and systems bound together by gravity carry negative gravitational potential energy. When you add up all the positive energy of every particle in every galaxy across the entire observable universe and combine it with all the negative gravitational energy binding those particles together, the total comes out to approximately zero. Alan Guth, the physicist who first developed the theory of cosmic inflation, called this the ultimate free lunch. 2 trillion galaxies, hundreds of billions of stars in each one, every planet, every ocean, every living creature, the entire magnificent structure of the cosmos may have a total energy bill of exactly nothing. The universe did not steal energy from somewhere else when it appeared. It simply organized zero into a very interesting shape. If this mechanism works once, there is no physical reason. It works only once. The quantum process that produced our universe is not a one-time event triggered by special circumstances. It is a consequence of how quantum mechanics operates at the deepest level of reality. And if it can happen once, it can happen again, and again, and again. Here's something worth thinking about. If the universe appeared without a cause, does that answer the question of why there is something rather than nothing, or does it simply reveal that the question needs to be asked in a completely different way? There is no physical reason this happened, only once. And when physicists work out how many times it could happen, the answer is not a large number. It is not even an astronomically large number. The answer is that it is happening right now, continuously, without end. And the scale of what that implies is something the next part of this story is about to make very difficult to ignore. In 1980, Alan Guth was a young physicist trying to solve 3 problems at once. The first was why the universe looks the same in every direction. Why 2 regions of sky on completely opposite sides of the cosmos have nearly identical temperatures, even though given the age of the universe and the speed of light, they could never have been in contact with each other long enough to reach the same temperature naturally. The second was why the large-scale geometry of the universe appears flat rather than curved, which requires the total energy density of the universe to sit at an extraordinarily precise value. The third was why certain exotic particles predicted by early universe physics don't seem to exist anywhere in the observable universe. 3 separate, independent problems, each requiring its own explanation. Guth found one mechanism that solved all three simultaneously. He called it inflation. The idea is that in the universe's earliest moments, a quantum field called the inflaton field drove space itself to expand at an exponential rate. Not matter moving through space, but space itself stretching so rapidly that in an almost incomprehensibly brief window of time, the universe went from a size smaller than a proton to something roughly the size of a grapefruit. That sounds unimpressive until you account for the fact that the expansion was exponential, doubling in size repeatedly within intervals of time so short they have no meaningful name in ordinary language. The smoothness, the flatness, the absence of exotic relics, inflation explained all of it in one stroke. And the predictions it made about the subtle temperature variations in the cosmic microwave background radiation were confirmed with extraordinary precision by the WMAP and Planck satellite missions decades later. Inflation is not a speculation, it is the best confirmed model of the early universe we have. But in 1983, André Linde noticed something in the mathematics of inflation that Guth had not fully accounted for. The inflaton field does not switch off everywhere. At the same time, quantum mechanics ensures that it decays in different regions at different moments. Randomly, the way a collection of radioactive atoms decays, not all at once, but one by one unpredictably. Each region where inflation stops becomes a bubble, a separate universe with its own properties, its own physical constants, its own history. Our universe is one such bubble. The moment inflation ended in our region, space stopped expanding exponentially and began the slower, gentler expansion we observe today. That transition, the moment our local inflation stopped, is what we experience as the Big Bang. But here is the crucial part. The regions where inflation has not yet stopped continue expanding exponentially, and exponential expansion is faster than the rate at which new bubbles form. Which means the total volume of still inflating space is always growing, always larger than the total volume of all the bubbles that have formed within it. The machine cannot turn itself off. No matter how many bubble universes appear, the inflating space between them grows faster than the bubbles can fill it. Inflation once started continues forever. Not in our bubble, but in the vast space surrounding it, the process is eternal. Our universe sits inside one of these bubbles, completely sealed off from the others. The space between any two bubble universes expands faster than light can cross it, which means no signal, no particle, no information of any kind can ever travel from one bubble to another. The other universes are not somewhere distant that we might reach one day with better technology. They are permanently, fundamentally unreachable. They exist, they are real, and they are as inaccessible as a number that has never been written down. Each bubble universe that forms inherits its physical constants from the specific way the inflaton field decayed in that region. A slightly different decay pattern produces a universe with different values for gravity, electromagnetism, the mass of the electron, the speed of light. Most of these universes are probably sterile gravity, too strong for stable orbits, electromagnetic force, too weak for chemistry, physical constants tuned in ways that prevent complexity from ever arising. But in an infinite collection of universes, every possible combination of constants appears somewhere, including the combination that produces stars, planets, chemistry, biology, and eventually creatures who build telescopes and ask questions about where everything came from. Eternal inflation is not an additional assumption layered on top of standard inflation. It is a mathematical consequence of standard inflation. If the inflaton field behaves the way quantum mechanics requires it to behave, and there is no reason to think it doesn't, then eternal inflation follows automatically. Accepting inflation without accepting eternal inflation would require the quantum behavior of fields to work differently in this one specific case than it works in every other case in physics. That is not a reasonable position. If countless universes are being created continuously right now, what does it mean for our universe to be special? Or are we simply one bubble that happened to form with the right conditions for someone to ask that question? Our universe may not be special at all. It may be one ordinary bubble among an infinite number of others, most of them dark and empty and cold, distinguished from the rest only by the fact that its particular combination of physical constants allowed something curious to develop inside it. But there is something else about our bubble that makes it unusual, not in the multiverse but in the history of physics. Our bubble may carry a scar. A faint geometric bruise pressed into the oldest light in the sky, left behind by a collision with another universe billions of years ago. And the evidence for that collision is already in our data, waiting to be confirmed. About 380,000 years after the Big Bang, something remarkable happened. The universe cooled just enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the universe was an opaque fog light, could not travel freely because it kept colliding with the sea of charged particles surrounding it. But when neutral atoms formed, the fog lifted. Light streamed out in all directions across the universe for the first time, and it has been traveling ever since. Today, nearly 14 billion years later, that ancient light reaches us from every direction in the sky simultaneously. We call it the cosmic microwave background radiation, and it is the oldest photograph of the universe that physics allows us to take. What makes this photograph extraordinary is not just its age, it is its precision. The temperature of this radiation is almost perfectly uniform across the entire sky. Not approximately uniform, not roughly uniform, but uniform to within 1 part in 100,000 degrees. Two regions of sky on completely opposite sides of the cosmos, so far apart that light from one could never have reached the other in the entire history of the universe, have temperatures that match each other to an almost impossible degree of accuracy. This uniformity is one of inflation's greatest predictions, and the data confirms it with stunning detail. But within that near-perfect smoothness, there are subtle variations, tiny hot and cold patches that encode the seeds of every galaxy, every star, and every planet that would form over the billions of years that followed. The cosmic microwave background is not just a photograph, it is a fingerprint. And some physicists believe it contains something more, traces of events that happened before our universe existed at all. When two bubble universes collide, the collision does not look like anything in ordinary experience. There is no explosion, no shockwave traveling through space, no visible flash of light. What happens is more subtle and more geometric. The boundary between two expanding bubbles when they meet creates a perfectly circular imprint on the interior of each bubble. From inside our universe, such a collision would appear as a disc-shaped region in the cosmic microwave background, a circular patch where the temperature is slightly warmer or slightly cooler than the surrounding sky, bounded by a clean, well-defined edge. The shape is not an accident. It is a direct consequence of the geometry of two spheres intersecting. A collision with another universe would leave a circular scar, and that scar would be written into the oldest light we can observe. In 2011, a team of physicists, led by Stephen Feeney, searched systematically through the WMAP satellite data, one of the most detailed maps of the cosmic microwave background available at the time, looking specifically for circular patterns consistent with bubble universe collisions. They found 4 candidate structures, 4 regions of the sky where the temperature profile matched the predicted signature of a collision with another bubble universe. The team was careful about their language. They did not claim discovery. They stated that the structures were consistent with collision signatures and that the probability of all 4 appearing by chance was low enough to warrant serious attention. The community responded with skepticism, counter-arguments, and alternative explanations. The debate was not resolved. But the structures did not disappear from the data. They remained unexplained, waiting for better instruments. Roger Penrose and Vahe Guzadian brought a different kind of anomaly to the conversation in 2020. Working within Penrose's cyclic cosmology framework, the idea that our universe is one in a sequence of universes, each born from the death of the previous one. They searched the cosmic microwave background for what Penrose called Hawking points. The prediction is specific: when a supermassive black hole in a previous universe evaporates completely through Hawking radiation, at the very end of that universe's life, the energy released creates a concentration of radiation that leaves a faint but detectable bright spot in the cosmic microwave background of the next universe. Penrose and Gerzadian reported finding anomalous bright points in the data consistent with this prediction, and they published their findings. The physics community pushed back hard, with several groups arguing that the signals could be explained by known statistical fluctuations in the data. Penrose disagreed with the counter-arguments. The debate continues, but here is the important point. Neither side has definitively closed the question. The data contains structures that some of the most serious physicists in the world consider worth explaining, and no consensus explanation exists. What is coming next may settle these questions permanently. The CMB-S4 experiment, a collaboration involving dozens of institutions and telescopes across the South Pole and Chile, is projected to begin full operations in 2027. The Lightbird satellite, developed by the Japan Aerospace Exploration Agency in collaboration with international partners, is scheduled for launch in 2028. Both instruments will map the cosmic microwave background with angular resolution and sensitivity roughly 10 times greater than current capabilities. Features that are currently ambiguous structures that could be collision signatures or could be statistical noise will become unambiguous. Either the circular patterns are real geometric features written into the oldest light in the universe, or they are fluctuations that sharper instruments will dissolve into the background. There will be no middle ground. The answer will be in the data. If the answer is yes, if CMB-S4 or Lightbird detects geometric structures that match the predicted signatures of bubble universe collisions, the implications reach far beyond any single scientific result in history. It would be the first direct observational evidence that our universe is not the only one. Not an inference, not a theoretical consequence, not a prediction that could be true in principle, but an actual measurement of a physical interaction between our universe and another. Every philosophical and scientific question about humanity's place in the cosmos would need to be asked again from the beginning, but confirmation would also raise a question that the collision hypothesis alone cannot answer. If our universe collided with another bubble universe, both bubbles had to exist inside the same inflating space for the collision to occur, which means both emerged from the same eternal inflation process. Which means the real question is not whether other universes exist alongside ours, but whether any of them existed before ours. Whether there was a universe before this one. Whether our Big Bang was not a creation event but a transition. The latest chapter in a story that has been running far longer than 13.8 billion years. Here's a question that cuts straight to the heart of it. If we find a scar on the sky left by another universe, does that mean our universe has a history that predates its own beginning? Bubble universes can collide. But there is a theory that goes further than collision. A theory that says our universe didn't emerge from inflation at all, in the way we usually picture it. It says our universe emerged from the corpse of a universe that died before ours was born. And that dead universe didn't vanish without a trace. It left something behind, a message written in light, encoded in the oldest patterns of the sky, waiting for someone inside the new universe to learn how to read it. Roger Penrose has spent decades being right about things that made other physicists uncomfortable. In 1965, he proved mathematically that black holes must contain singularities, points where the known laws of physics break down completely. The physics community resisted the idea for years before the evidence became undeniable. In 2020, he received the Nobel Prize in Physics partly for that work. So, when Penrose proposes something that sounds outrageous, it is worth paying close attention to the mathematics behind it. What Penrose proposes now is this: our universe is not the first. It will not be the last. What we call the Big Bang was not the absolute beginning of existence. It was a transition point, a moment of rebirth, the opening chapter of a new cosmic cycle that follows from the death of the one before it. He calls this framework conformal cyclic cosmology, and the argument for it begins not with the beginning of the universe, but with its end. Picture the universe in its final state, not billions of years from now, but trillions upon trillions of years from now, at a scale of time that makes the current age of the universe look like the first second of a human life. By that point, every star has exhausted its fuel and gone dark. Every proton, if current theoretical predictions are correct, has decayed. Every black hole, no matter how massive, has slowly evaporated through Hawking radiation and disappeared. What remains is a universe containing nothing but photons and other massless particles drifting through an expanding void, growing ever colder, ever more dilute, separated by distances so vast that the concept of proximity has lost all meaning. Here is where Penrose's insight becomes extraordinary. Massless particles, particles with no mass whatsoever, do not experience time in the way that massive objects do. They travel at the speed of light, and at the speed of light, time does not pass. A photon emitted from a star and traveling across the universe for 10 billion years experiences zero duration between its emission and its absorption. From the photon's perspective, those 10 billion years simply do not exist. In a universe containing only massless particles, the concept of scale also becomes meaningless. Without mass, there is no way to define a ruler or a clock. The enormous, ancient, cold, dying universe and the tiny, hot, dense, newborn universe that follows it become mathematically identical, not similar, not analogous. Identical in a precise technical sense that Penrose expresses through a branch of mathematics called conformal geometry, which preserves angles and shapes but not sizes. The death of one universe and the birth of the next are the same event described from two different perspectives. The Big Bang that created our universe was the heat death of the universe that came before it. This is not a metaphor. The mathematics is specific and testable. If Penrose is correct, the collisions between supermassive black holes in the previous cosmic cycle events of almost unimaginable violence, in which objects billions of times more massive than our Sun spiral together and merge would have, sent gravitational waves rippling outward across the entirety of that dying universe. Those gravitational waves would have survived the transition between cycles and left circular patterns in the cosmic microwave background of our universe. Concentric rings slightly cooler or warmer than the surrounding radiation centered on the point in our sky that corresponds to where each ancient collision occurred. Penrose and his colleague Vahe Gurzadyan searched the existing cosmic microwave background data and reported finding structures consistent with these predictions. The debate over their statistical significance continues, but the prediction itself is unambiguous, and the next generation of instruments will test it directly. A completely separate line of thinking arrives at a similar conclusion through different mathematics. Loop quantum cosmology, a framework that attempts to apply quantum mechanics to space and time themselves, finds that the mathematical singularity at the beginning of the universe is an artifact of using classical physics in a regime where quantum effects dominate. When you apply quantum corrections to the equations governing the collapsing universe, the singularity disappears. Instead of space and time collapsing to a point of infinite density and the equations breaking down, the universe reaches a maximum density, an extraordinarily high but finite density, set by the fundamental quantum properties of space and density, then bounces. The collapse becomes an expansion. The crunch becomes a bang. Our universe did not appear from nothing. It rebounded from the extreme compression of a previous universe that had collapsed under its own gravity, the Big Bounce. Loop quantum cosmology makes predictions that differ from standard inflation in the spectrum of primordial gravitational waves, ripples in space-time generated in the earliest moments of the universe's existence. The pattern left in the cosmic microwave background by these waves has a specific shape that depends on whether the universe emerged from inflation or from a bounce. The difference is subtle but measurable, and the instruments coming online in the late 2020s are precisely the tools needed to tell the two scenarios apart. If either Penrose's cyclic cosmology or the Big Bounce picture is correct, the universe we inhabit is not the first generation. It is the latest in a sequence generation n of a process that may have been running for a duration that has no relationship to any number human language has a word for. We do not know what n is. We do not know if there is a first generation or if the sequence is infinite in both directions. We are living inside one chapter of a story whose beginning, if it has one, is beyond the reach of any instrument we can imagine building. The universe keeps dying and coming back to life, which honestly sounds less like a physics theory and more like a Hollywood action franchise. Except in this franchise, every sequel is at least as good as the original. If our Big Bang was a transition rather than a beginning, if something existed before it, what determined the rules of physics that our universe was born with? Who set the parameters for this particular cycle? That question cuts deeper than it first appears. Because the rules of our universe, the strength of gravity, the mass of the electron, the speed of light, are not arbitrary. They are exquisitely tuned. And the answer to what determines them may lie not in the history of the universe, but in its hidden geometry. In dimensions of space that have been there all along, curled up tightly enough that no instrument has ever directly detected them, yet responsible for every physical law we have ever measured. Take every particle that has ever been discovered: electrons, quarks, photons, neutrinos, the Higgs boson, every entry in the standard model of particle physics, and ask what they actually are at the most fundamental level. Classical physics says they are point-like objects with no internal structure, but that picture produces mathematical infinities that cannot be resolved, and physicists have spent decades trying to replace it with something better. String theory offers a replacement that is either the deepest insight in the history of physics or the most elaborate wrong answer ever constructed. And the argument over which of those it is has been running for 40 years without resolution. The core idea is simple enough to state in one sentence: every fundamental particle is not a point. It is a tiny loop of energy, a string vibrating at a specific frequency. Different frequencies produce different particles. An electron is a string vibrating one way. A photon is the same kind of string vibrating differently. A quark is another vibrational pattern entirely. The entire particle zoo of the standard model, dozens of distinct particles with dozens of distinct properties, collapses into a single object whose different modes of vibration account for all the variety. One instrument, one string playing every note in the universe simultaneously. The mathematical consistency of string theory comes at a price. The equations only work without internal contradictions if space has more dimensions than the 3 we experience, not slightly more. The mathematics requires 10 or 11 dimensions of space for the theory to be self-consistent. Since we clearly only move through 3 spatial dimensions in our daily experience, the remaining 6 or 7 must be hidden. String theory proposes that they are curled up, compactified into structures so small that even the most powerful particle accelerators cannot probe them directly. These hidden dimensions are not empty geometrical abstractions, they have shapes, and those shapes matter enormously. The hidden dimensions in string theory are described by mathematical objects called Calabi-Yau, manifolds, complex 6-dimensional shapes with intricate internal geometry. Here is the crucial point. The specific shape of the Calabi-Yau manifold in a given universe directly determines the physical constants of that universe. The way the hidden dimensions are folded controls how strongly gravity pulls, how massive the electron is, how the electromagnetic force behaves, how nuclear forces hold atoms together. Change the shape of the hidden dimensions, and you change every physical law simultaneously. A universe with a different Calabi-Yau geometry is not just a universe with slightly different constants. It is a universe where the entire character of physical reality is different, where atoms may not be stable, where stars may not form, where chemistry as we know it is simply impossible. This connection between hidden geometry and physical law becomes the foundation for one of the most striking proposals about cosmic origins. In 2001, physicists Paul Steinhardt and Neil Turok developed what they called the ekpyrotic model. Their starting point was not inflation, but the higher dimensional framework of string theory, specifically the idea that our universe is a 3-dimensional membrane, called a brane, floating in a higher dimensional space. Picture 2 enormous flat sheets, separated by a tiny gap in a dimension we cannot perceive. Each sheet is a universe. Our universe is one of them. The other sheet has been there all along, parallel to ours, separated by a distance smaller than the width of a proton in the hidden dimension between them, completely invisible to us, completely real. In the ekpyrotic model, these 2 branes attract each other gravitationally across the hidden dimension, separating them. Over an immense span of time, they drift toward each other. When they collide, the collision releases a staggering quantity of energy across both surfaces simultaneously. From inside our brain, from inside our universe, that energy release looks exactly like a Big Bang. Space fills with hot, dense matter and radiation. The expansion begins. Our universe is born. Not from nothing. Not from a quantum fluctuation. From the collision of two physical objects in a space, with more dimensions than we can perceive. And the collision does not destroy the brains. They bounce apart, cool down, and slowly drift toward each other again. Over another vast span of time, measured not in billions but in thousands of billions of years, they approach, collide again, and the cycle repeats. This is a completely different mechanism for a cyclic universe than the one Penrose describes, arriving at a similar conclusion from a completely different direction. Two independent paths through very different mathematics, both suggesting that our Big Bang was not the first and will not be the last. In 1995, Edward Witten showed something that unified the entire landscape of string theories. There had been 5 different versions of string theory, each mathematically consistent, each seemingly distinct. Witten demonstrated that all 5 are actually the same theory, viewed from different perspectives, different limiting cases of a single 11-dimensional framework he called M-theory. The unification was one of the most significant theoretical achievements of the late 20th century. It also deepened the mystery of the hidden dimensions, because M-theory's 11th dimension is the one through which the brans of the ekpyrotic model move and collide. If the shape of hidden dimensions determines the physical laws of a universe, what determined the shape of our hidden dimensions? Was it fixed at the moment of the Big Bang, inherited from a previous cycle, or chosen randomly from an enormous landscape of possibilities? The answer may be that nothing chose it at all. Every possible shape may already exist, every possible set of physical laws, every possible universe, all of them equally real. And that possibility leads to something even stranger than hidden dimensions, the discovery that the 3-dimensional space we live in may not be fundamental at all. It may be a projection, a shadow cast by information stored on a surface we can never reach in a reality that is at its deepest level 2-dimensional. There is a question that sounds like it belongs in a philosophy seminar rather than a physics department. Is the 3-dimensional space you are sitting in right now actually real? Not real in the sense of being a useful description of your experience. Clearly, it is that. Real in the sense of being fundamental. Real in the sense of being the deepest layer of physical existence rather than something that emerges from something deeper. For most of the history of science, this question would have been dismissed as untestable speculation. Then black holes forced physicists to take it seriously, and what they found there changed the foundations of everything. The story begins with entropy. In thermodynamics, entropy is a measure of how much information is needed to completely describe the internal state of a system. A glass of water has enormous entropy because the precise positions and velocities of every molecule inside it would require an almost incomprehensible amount of information to specify fully. Intuitively, the entropy of any object should scale with its volume. The more space something occupies, the more internal states it can have, the more information it takes to describe it completely. This is true for everything in ordinary experience. But in the early 1970s, physicist Jacob Bekenstein discovered that black holes do not follow this rule. The entropy of a black hole is proportional not to its volume but to the area of its surface, its event horizon. Not approximately proportional, exactly proportional. This result, later refined by Hawking, is one of the most precisely established results in theoretical physics. The implications took years to fully sink in. If the information content of a black hole, which is after all a 3-dimensional object with a genuine interior, is completely encoded on its 2-dimensional surface, then the 3-dimensional interior is not adding any new information. Everything happening inside the black hole is already fully described by what is written on its boundary. The interior is redundant. It contains nothing that the surface doesn't already tell you. In 1993, Gerard Hooft, who would receive the Nobel Prize in Physics 6 years later, drew the logical conclusion from this. If it works for black holes, it should work for any region of space. The complete physical description of any 3-dimensional volume should be encodable on the two-dimensional surface surrounding it. He called this the holographic principle, and it suggested something deeply strange about the nature of space itself. The principle might have remained an interesting but unverified speculation if Juan Maldacena had not published a paper in 1997 that gave it a precise mathematical foundation. Maldacena demonstrated an exact equivalence between two completely different physical theories. On one side, a theory of gravity operating in a five-dimensional space with a specific geometry. On the other side, a quantum field theory with no gravity whatsoever living on the four-dimensional boundary of that space. These two theories are not similar. They are not analogous. They are exactly equivalent. Every calculation you can perform in one has a precise translation in the other, and both give identical answers. The paper became the most cited work in the history of theoretical physics. The correspondence it describes is called ADS, CFT, and it has been tested in thousands of calculations over the following decades without a single inconsistency. The implications of Maldacena's result are staggering. If a universe with gravity is exactly equivalent to a lower dimensional theory without gravity, then gravity itself is not fundamental. It is emergent. It arises from the behavior of quantum systems on a boundary, the way temperature arises from the collective motion of atoms. The three-dimensional space we move through, the gravitational field that keeps planets in orbit and holds galaxies together, the curvature of space-time that Einstein spent a decade discovering, all of it may be a higher dimensional projection of information encoded on a surface we cannot directly observe. Three-dimensional space and gravity are not the bedrock of reality. They are the shadows that bedrock casts. Mark van Ramsdonk pushed this further in 2010 with a thought experiment that became one of the most discussed papers in theoretical physics that year. Take two separate quantum systems with no physical connection between them. Now, allow them to become quantum entangled, linked in the way quantum mechanics permits, where the state of one system is correlated with the state of the other regardless of the distance between them. Van Ramsdonk showed that in the holographic framework, this entanglement corresponds to the emergence of a spatial connection between the two systems, essentially a bridge through space. Now cut the entanglement. Reduce the quantum correlations between the two systems to zero. The spatial bridge disappears. The space connecting them is destroyed. The conclusion is unavoidable. Space is not a container that exists independently and then gets filled with quantum systems. Space is what quantum entanglement looks like when you stand back far enough to see the geometry it creates. Entanglement is not something that happens in space. Space is something that happens because of entanglement. This reframes the question of what existed before the Big Bang in a way that cuts through the usual confusion. If space is emergent, if it arises from quantum entanglement rather than existing independently, then before the Big Bang, when the universe was in its most extreme initial state, the question is not, what was the space like before everything began? There was no space before everything began in the sense of there being no pre-existing container waiting to be filled. The question becomes something more precise and more tractable. What was the quantum informational state from which space, time, and matter all emerged together? Before the Big Bang is not a location. It is not a time. It is a description of a quantum state, a configuration of information that had not yet organized itself into the geometry we recognize as three-dimensional reality. If three-dimensional space emerges from quantum entanglement, what is actually real, at the deepest level beneath the space, beneath the entanglement, beneath everything we can directly measure? The answer that keeps appearing across multiple independent lines of research is the same one word: information. And information turns out to have a property so strange, so absolute, and so consequential that it changes every question about origins and endings simultaneously. Information, it turns out, cannot be destroyed, not by fire, not by time, not even by the most destructive objects in the universe. And the proof of that statement came from a bet that Stephen Hawking lost. In 1976, Stephen Hawking published a calculation that created the biggest crisis in theoretical physics of the 20th century. He had already shown several years earlier that black holes are not entirely black, They emit a faint thermal radiation as a consequence of quantum effects near the event horizon, a result now universally known as Hawking radiation. The new calculation extended this result to its logical conclusion. If a black hole continuously radiates energy, it must slowly lose mass. Over an immense span of time, it shrinks. Eventually, it evaporates completely and disappears. And the radiation it emits in the process Hawking showed is perfectly thermal. It carries no information about what fell in. A black hole that swallows an encyclopedia and a black hole that swallows the same mass in plain hydrogen gas would both produce identical radiation as they evaporated. The encyclopedia's contents would be gone forever. Information would be destroyed. This was not a minor technical point. It was a collision between the two greatest theories in physics. Quantum mechanics rests on a foundation that includes the principle that information is always conserved, that the complete quantum state of a system at any moment contains in principle enough information to reconstruct the complete state at any other moment, past or future. Hawking's calculation said black holes violate this principle absolutely. One of the two theories had to be wrong. For nearly 3 decades, physicists argued about which one. In 2004, at a conference in Dublin, Hawking conceded. He had found a new way of calculating the process of black hole evaporation using a sum over all possible geometries of spacetime rather than a single fixed background. The result was different. Information was not destroyed. It was scrambled, transformed into the most complex, most thoroughly mixed form imaginable, but it was preserved in the correlations between the particles of Hawking radiation emitted over the black hole's entire lifetime. To recover the original information would require measuring every particle the black hole had ever emitted, understanding the quantum correlations between all of them simultaneously, and performing a calculation of complexity that no conceivable technology could execute. But the information was there. It had never left. Hawking acknowledged his error publicly, paid his debt in the bet he had made with physicist John Preskill, and handed over a baseball encyclopedia. The technical mechanism behind information's escape from a black hole involves what physicists call page time, named after Don Page, who identified it in 1993. When a black hole first forms and begins evaporating, the early Hawking radiation carries essentially no information about the black hole's interior. The radiation appears genuinely random, but at the halfway point of the evaporation, page time, something shifts. The remaining radiation and the already emitted radiation become increasingly correlated. Information that was scrambled into the black hole's internal state begins leaking out, hidden in the quantum correlations between particles that were emitted at very different times. By the time the black hole has completely evaporated, every bit of information that ever fell in has been re-emitted, encoded in a form of extraordinary complexity but complete fidelity. Nothing was lost. If information is truly conserved without exception, if not even the most extreme physical process in the universe can destroy it, then the consequences reach far beyond black hole physics. Every quantum interaction that has ever occurred in the history of the universe has left a permanent record encoded somewhere in the quantum state of the universe as a whole. The state of matter in the first moments after the Big Bang, and if the cyclic and bounce models discussed earlier are correct, the state of whatever existed before the Big Bang is encoded in the current quantum state of the universe, not accessible with any instrument we currently possess, not recoverable with any technology we can currently imagine, but there, present, preserved with perfect fidelity in the structure of physical reality. John Wheeler, the physicist who coined the term black hole and spent the last decades of his career thinking about the deepest nature of reality, proposed a framework he called it from bit. The name is compact, but the idea is radical. Every physical thing, every particle, every field, every force, every interaction derives its existence from information. Not from matter that happens to carry information as a secondary property, but from information in itself at the most fundamental level. The universe is not a collection of physical objects that generate information as a byproduct. The universe is information, and physical objects are what certain configurations of information look like when they interact with other configurations of information. Seth Lloyd at the Massachusetts Institute of Technology took this idea and made it quantitative. He calculated the total number of elementary logical operations, the most basic possible information processing steps that the observable universe has performed since the Big Bang. The answer is approximately 10 raised to the power of 120. That number is the computational history of everything that has ever happened, expressed as a count of the simplest possible operations at the quantum level. The universe in this picture is not like a computer. It is a computer, the largest and most complex information processing system we know of, running a program whose output is physical reality as we experience it. This picture transforms the question of cosmic origins one final time. Before the Big Bang is no longer a question about empty space, or about a previous universe, or about a quantum vacuum fluctuation in a void. It is a question about the initial conditions of an information processing system. What was the starting state of the computation? What information was present before space and time organized themselves into the universe we inhabit? The question is still unanswered, but it is now, for the first time, precisely stated. If information is the most fundamental thing in existence, where did the original information come from? Who wrote the starting conditions of the universe? The boldest answer in the history of physics says, nobody wrote it. Because it was never created. Because it was always there, not in space, not in time, but in a realm that exists prior to both and independent of both. A realm that physics has been describing with extraordinary precision for centuries without quite realizing what it was describing. That realm is mathematics. And the claim that mathematics is not a tool we invented to describe reality, but the actual fabric from which reality is made, is about to become the most important idea in the final act of this story. In 1960, the physicist Eugene Wigner published an essay with a title that has haunted science ever since. He called it The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The question he posed was simple and remained unanswered. Why does mathematics, developed entirely inside human minds, often for purely abstract reasons, with no connection to physical reality, describe the physical world with such extraordinary, almost unsettling precision? This was not a rhetorical flourish. It was a genuine puzzle that cut to the heart of what science is actually doing when it works. Consider the history of complex numbers. Mathematicians invented them centuries ago to solve equations that had no solutions in ordinary arithmetic equations involving the square root of negative numbers, quantities that seem to have no physical meaning whatsoever. For a long time, complex numbers were considered a purely formal trick, a useful fiction that helped with calculations but corresponded to nothing real. Then, quantum mechanics was developed in the 1920s, and physicists discovered that complex numbers are not a convenient tool for describing quantum systems. They are the native language of quantum systems. The wave function that describes the quantum state of every particle in the universe is fundamentally complex-valued. Remove complex numbers and quantum mechanics does not become harder to express. It becomes impossible to express. Nobody designed this. Nobody planned for the abstract invention of one era to become the indispensable foundation of physics centuries later. The same story repeats with non-Euclidean geometry. In the 19th century, mathematicians developed geometries in which the parallel postulate of Euclid does not hold spaces that curve in ways flat geometry cannot describe. This was considered a purely theoretical exercise, an exploration of logical possibility with no connection to physical reality. Then Einstein developed general relativity, and it turned out that the geometry of space-time, the actual structure of the universe we inhabit, is precisely the non-Euclidean geometry that mathematicians had developed as an abstract curiosity decades earlier. The mathematics was waiting for the physics to catch up, as if it already knew. Max Tegmark, a cosmologist at the Massachusetts Institute of Technology, takes this pattern seriously enough to follow it to its logical conclusion. His proposal is called the mathematical universe hypothesis, and it states something that sounds extreme until you sit with it long enough to feel its force. The universe does not follow mathematical laws. The universe does not merely correspond to a mathematical structure. The universe is a mathematical structure. Physical existence and mathematical existence are not two different things with a correspondence between them. They are the same thing described from two different perspectives. Every electron, every photon, every quantum field, every force, these are not physical objects that happen to obey equations. They are mathematical objects, and the equations are not descriptions of something else. The equations are something else. If this is correct, the question, why does mathematics describe physics so well, dissolves completely. It describes physics well for the same reason that a map of a city matches the city's streets. Not because someone carefully designed the correspondence, but because the map and the city are the same thing represented in two different ways. We have been writing equations about the universe, and then going out to check whether the universe agrees. The reason it always agrees is that we were never writing about something separate from the equations. We were writing the equations that constitute the thing we were checking against. The implications for the question of cosmic origins are immediate and striking. If every self-consistent mathematical structure exists as a physical universe, then the answer to what existed before the Big Bang is not a prior universe, not a quantum vacuum, not a cyclic predecessor. The answer is that the entire landscape of mathematical structures, infinite in scope, containing every possible set of physical laws, every possible geometry, every possible history, already existed outside of space and outside of time, because mathematical truths do not require space or time to be true. The theorem that the angles of a triangle sum to 180 degrees in flat geometry was true before any universe existed to contain a triangle. In the same way, the mathematical structure that we call our universe was part of the timeless landscape of all possible mathematics, long before the Big Bang organized it into something that contains observers. The Big Bang in this picture was not a creation event. It was the moment when a particular mathematical structure became complex enough, rich enough, internally developed enough to contain within itself entities capable of observation. Not the moment the structure began to exist. It always existed in the same sense that all mathematical truths always exist. The moment it began to contain observers who could look around and ask where everything came from. And this leads to a question about mathematical nothingness that turns out to be self-defeating. Could there have been nothing, not just no universe, but no mathematics either? The answer appears to be no, for a reason that is almost too clean to be comfortable. Nothing is itself a mathematical concept. A state of complete absence containing no objects, no relations, no structure whatsoever is a precisely defined mathematical notion, and as a mathematical notion it exists within the landscape of all mathematical structures. True nothingness, if it were a coherent concept, would be a self-consistent mathematical structure and would therefore, by Tegmark's hypothesis, correspond to a physical reality. But a physical reality of complete nothingness is a contradiction in terms. Mathematical nothingness undermines itself the moment you try to define it rigorously. Something had to exist, not because something created it, but because the alternative is logically incoherent. Turns out the high school math teacher was right all along when they said you'd use this stuff later. They just didn't specify that later meant as the foundation of every possible reality that could ever exist. If every self-consistent mathematical structure exists as a real universe, what makes our particular universe feel real to us, rather than just one abstract structure among infinitely many others? That question points directly at the one thing physics has spent most of its history trying to avoid talking about. The one variable in the equations of quantum mechanics that nobody fully understands. The one concept that keeps appearing at the boundary between possibility and actuality, between the quantum superposition of all states and the single definite reality we experience, consciousness. And when physics is finally forced to look at it directly, what it finds there is stranger than anything that has come before. Here is an experiment that has been performed thousands of times in dozens of laboratories with electrons, photons, atoms, and molecules, always with the same result. Fire a single electron at a barrier with two narrow slits cut into it. Place a detector screen on the other side. Do this repeatedly, one electron at a time, and watch where the electrons land. What you find is an interference pattern. a series of alternating bands where many electrons land and bands where almost none land. The pattern is the signature of a wave passing through both slits simultaneously, the two parts of the wave interfering with each other on the far side. But you are firing individual electrons. Each electron somehow passes through both slits at once, interferes with itself, and produces a pattern that only makes sense if each electron explored every available path simultaneously. Now, add a detector at the slits, any device capable of recording which slit the electron actually passes through. The interference pattern immediately disappears. The electrons begin landing in two simple bands, one behind each slit, exactly as classical particles would. The act of measuring which path the electron took has changed what the electron does. The electron is not secretly taking one path, and we are simply ignorant of which one. Every careful analysis of the experimental results confirms that before measurement, the electron genuinely has no definite path. Both possibilities are simultaneously real. Measurement makes one of them definite and the other one cease. John Wheeler took this further with a variation he called the delayed choice experiment. Set up the apparatus so that the decision of whether to measure which slit the electron used is made after the electron has already passed through the barrier. After, in any classical sense, the electron's path is already determined. The result is the same as before. Choosing to measure retroactively eliminates the interference pattern. Choosing not to measure retroactively allows it. The future decision of whether to observe appears to reach backward in time and change what the electron did in the past. This is not a paradox born of sloppy thinking. It is what the mathematics predicts and what the experiments confirm. The timeline of cause and effect, as it applies to quantum systems, does not run only forward. The measurement problem sits at the center of this. In quantum mechanics, a system exists in a superposition of all possible states until it is measured, at which point it transitions to a single definite state. This transition, called the collapse of the wave function, is built into the standard formulation of quantum mechanics as a postulate. It happens. But the theory does not say what counts as a measurement. Does a photon colliding with an atom constitute a measurement? Does a Geiger counter clicking? Does a camera recording an image? Does a human looking at the camera's output? Physicists have debated this since the 1920s without reaching consensus. The boundary between quantum superposition and classical definiteness has no agreed location, and different answers to where that boundary sits lead to radically different pictures of what reality is. Hugh Everett's many worlds interpretation, proposed in 1957, eliminates the collapse entirely. The wave function never collapses. Every possible outcome of every quantum measurement happens in a separate branch of a constantly splitting universe. When you measure which slit the electron passed through, both outcomes occur in two branches that immediately become unable to interact with each other. You find yourself in one branch. The other version of you finds themselves in the other. The universe does not choose, it bifurcates. This interpretation preserves the mathematical simplicity of quantum mechanics at the cost of an almost incomprehensible proliferation of parallel realities, each as real as the one you are experiencing now. Wheeler's own interpretation moved in a completely different direction. He called it the participatory universe, and it placed the observer not at the end of the physical process, but at its center. In Wheeler's picture, the universe produces observers through billions of years of cosmic and biological evolution, and those observers, through the act of quantum measurement, participate in giving the universe a definite history. The universe and its observers are not separate. They are locked in a loop. The universe creates the conditions for observers to exist, and observers, by observing, help determine which history the universe actually has. The cosmic past is not fully written until something capable of observation exists to write it. The cosmological implications of this are genuinely disorienting. If the early universe, before any stars had formed, before any planets existed, before any life had evolved, existed in a quantum superposition of all possible histories, then its specific history may not have been determined at that time. It may have remained genuinely indeterminate, a superposition of all possible cosmic evolutions, until the first observers appeared, and their measurements began collapsing the quantum possibilities into a specific past. In this reading, the 13.8 billion years of cosmic history that preceded your existence were not a sequence of definite events that led to you. They were a cloud of quantum possibilities that your existence and the existence of every other observer is continuously collapsing into a specific story. You are not the product of a history. You are, in a precise, quantum mechanical sense, partially responsible for determining what that history is. This is not mysticism dressed in physics language. It is a straightforward reading of what quantum mechanics says about the relationship between measurement and reality applied at the largest possible scale. It may be wrong. The many worlds interpretation, if correct, would dissolve the problem entirely by making every history equally real without requiring observers to select among them. The measurement problem remains genuinely unsolved, which means the role of consciousness in quantum mechanics remains genuinely open. But the question itself, whether observers are passive recorders of a pre-existing reality or active participants in constituting it, is one of the most consequential open questions in all of science. If observers help determine the history of the universe through quantum measurement, does your existence right now reach backward through 13.8 billion years and participate in writing the story of how everything began? Physics cannot yet answer that question. But here is what it can say with confidence. Whether the universe ends in the slow freeze of heat, death in the violent, tearing apart of every structure that exists, or in the compression and rebound of another Big Bang, the act of asking these questions is itself part of what the universe is doing. Something made of atoms and energy that was created in the first moments of cosmic history has organized itself after nearly 14 billion years into a form that can look back at its own origin and ask why. Whatever the answer turns out to be, that fact alone is among the most remarkable things about the universe we inhabit. Every story needs an ending, but the universe, it turns out, may not have agreed to that arrangement. 3 possible fates wait at the end of cosmic time, and which one arrives depends on a single quantity that humanity has been measuring for less than 30 years. The behavior of dark energy, the mysterious force driving the accelerating expansion of space. The first possibility is heat death. Expansion continues forever, slowly and relentlessly, until every star in every galaxy exhausts its fuel and goes dark. The last red dwarfs flicker out after a duration so long it makes the current age of the universe look like a single heartbeat. Black holes, now the only significant structures remaining, slowly evaporate through Hawking radiation over timescales that dwarf even that. Eventually, the last black hole disappears in a faint burst of radiation, and what remains is a universe of isolated elementary particles drifting through an infinite, cold, perfectly dark void, separated by distances that grow larger every moment, never to interact again. Not destruction, just silence. The universe does not end. It simply becomes too spread out to do anything. The second possibility is more violent. If dark energy grows stronger over time, rather than remaining constant, the expansion of space accelerates without limit. At first, distant galaxies recede faster than light and vanish from our observable sky, which is already happening. Then, as the acceleration intensifies, the expansion tears apart gravitationally bound structures that have survived until now. Galaxy clusters are pulled apart, then individual galaxies, then solar systems, then planets. Then, in the final moments of this scenario, estimated at roughly 22 billion years from now, the force of expansion overcomes the electromagnetic bonds holding atoms together, and matter itself is shredded at the subatomic level. Space tears itself apart in what physicists call the Big Rip. Not a slow fade, but a violent unraveling ending in a moment of infinite expansion that destroys every structure in existence simultaneously. The third possibility loops back to everything discussed earlier. If dark energy weakens or reverses, expansion slows, stops, and gravity reasserts itself. The universe collapses inward over billions of years, growing hotter and denser as it contracts until it reaches the extreme conditions of the Big Bounce described by loop quantum cosmology, and rebounds into a new Big Bang, a new universe, a New cycle of cosmic history. In 2024, the Dark Energy Spectroscopic Instrument, a survey instrument mounted on a telescope in Arizona, mapping the three-dimensional positions of tens of millions of galaxies, released its first major results. The data suggested something that no previous observation had clearly shown: dark energy may not be constant. Its strength appears to have varied over cosmic time, behaving differently in the earlier universe than it does today. If confirmed by subsequent observations, this would be the first direct evidence that dark energy is not a fixed property of empty space, but something dynamic, something that evolves. And if it evolves, every prediction about the long-term fate of the universe needs to be reconsidered from the beginning. The game, as it turns out, is still being played. The ending has not been written, but here is something worth holding on to, regardless of which fate the universe is heading toward. If the cyclic models are correct, if our universe is one in a sequence of cosmic generations, then the information encoded in the quantum structure of our universe does not simply vanish when it ends. Information, as established earlier, cannot be destroyed. The quantum state of everything that has ever happened in our universe, every particle interaction, every structure, every thought encoded in the neural patterns of every conscious being that has ever lived, is woven into the fabric of physical reality with perfect fidelity. In a cyclic scenario, the conditions of the next universe inherit something from the current one. A form of cosmic heredity passed from one generation of reality to the next, each cycle shaped in some way by the one that preceded it. Now step back and look at the full journey this story has traveled. Absolute nothingness is physically forbidden. The universe cannot come from true nothing, because true nothing cannot exist, even as a theoretical state. Quantum fluctuations can produce a universe without a cause, without a preceding moment in time, without violating a single conservation law. Eternal inflation means that process never stops producing an endless proliferation of bubble universes, with different physical laws in a space that grows faster than any count of new universes can keep up with. Space itself is not fundamental. It emerges from quantum entanglement, which means before the Big Bang is not a location in space, but a description of an informational state that had not yet organized itself into geometry. Information is the deepest layer of physical reality, indestructible and complete, encoding every event that has ever occurred. Mathematics exists independently of space and time, and may be the substance from which physical reality is made, rather than the language we use to describe it. And then, after nearly 14 billion years of cosmic evolution, stars burning planets, forming chemistry, complexifying biology, emerging, the universe produced something that looks back at all of this and asks why. That last step is the strangest one, not because consciousness is mysterious, though it is, but because of what it implies about the relationship between the universe and the questions it generates. Every atom in your body was forged inside a star that died before the solar system existed. The carbon in your cells, the calcium in your bones, the iron in your blood, all of it was created by nuclear fusion in stellar cores and scattered across space by supernova explosions over billions of years. You are not separate from the universe looking at it through a window. You are the universe, locally organized into a configuration that can perceive, think, and ask questions. When you wonder what existed before the Big Bang, the universe is wondering about its own origin through the only instruments it has ever produced that are capable of wondering minds made of the same matter the Big Bang created. The question, what came before the Big Bang, may never receive a complete answer. Not because science is inadequate, and not because the answer is hidden beyond some permanent barrier, but because the question, as it is usually posed, assumes a conceptual framework: cause before effect, space as a pre-existing container, time as an infinite line, extending in both directions, that the physics we have developed over the past century has quietly dismantled. Every time physics reaches what looks like a final wall, it finds not a dead end, but a door into a larger room. Classical mechanics gave way to relativity. Relativity gave way to quantum mechanics. Quantum mechanics points towards something: quantum, gravity information, geometry, the holographic principle that we are still learning how to ask questions about. The next room is always bigger than the last. This is not a place where the story ends. It is a place where a different kind of story begins. The questions that will define the next century of physics are questions we do not yet have the language to ask clearly. The instruments being built right now, CMB, S4 Light BID, next-generation gravitational wave detectors, will return data that may force entirely new frameworks into existence. The answers will not simply fill in the blanks on the picture we currently have. They will change the picture itself, the way every genuine scientific revolution has always changed the picture. Out of everything physics has revealed in this story, the boiling void, the universe tunneling from nothing, the infinite factory of bubble universes, space emerging from entanglement, information that cannot die, mathematics as the fabric of existence, consciousness as the universe looking at itself. Which one keeps pulling at you? Which one do you find yourself still thinking about long after everything else has faded?